So the last speaker for this session is Grong, who is going to talk about geometric rough path on Hilbert spaces. Please.
Hi, thank you very much. I would like to thank the organizers for giving me the opportunity to speak. So this is the first time I do any kind of research into rough path theory. So luckily I have worked with Torstein Nielsen and Alexander Schmedding with this project. And what we're going to talk about is weakly geometric rough paths and geometric rough paths in Hilbert spaces. So just recall some definition and just to showcase the notation I'm using. So recall that okay, if we have a finite dimensional space, a alpha rough path, alpha Hilbert rough path is a curve in the truncated tensor algebra. So I will just stop at, I will also always have alpha between a third and a half. So stop at step 2. And it continues with respect to this distance here, where I'm making this distance defined like this from the identity and defining that it's left invariant with respect to the tensor multiplication, truncated tensor multiplication. So it's, today we're only going to talk about things that are at least weakly geometric. So meaning that the symmetric part here, which is, this is twice the symmetric part, is equal of the second order term is equal to the tensor product of the first order term with itself. And then we finally have geometric rough paths, which are closures of signatures of paths of finite variation in this alpha Hilbert metric. So in particular, this, by just using standard integration tricks, geometric rough paths are weakly geometric rough paths. So the other way around, the relation is given as follows. If you have a weakly geometric rough path, then it will be a geometric rough path if you lower the Hilbert exponent ever so slightly. Yeah, so this this also holds when you're for lower Hilbert exponents, but we're only sticking with things between 1/2 and 1/3 today. And what we're going to talk about today is that this result also holds when E is a Hilbert space. So when we have a rough path in Hilbert space, when our tensor product is defined with respect to the projective norm. So that's what we're going to talk about today. In order to discuss this in more detail, I will first need to explain what the words I said mean. So we're going to have to talk about rough paths on Banach spaces in general, infinite dimensional spaces. So everything that I presented before still makes sense in an infinite dimensional space, and says, except that there's an ambiguity of what the tensor product actually is. So we need to discuss about that. Then we need to, in order to talk about the actual proof, we need to talk about the Kanoko-Theodori metric. So that's what I usually work with is like this Kanoko-Theodori geometry or Subramanian geometry. And we'll discuss how that works and why my background doesn't actually help me that much with this problem, unfortunately, when we come to infinite dimensions. And then I will end with discussing some applications to rough flows from our results. So let's talk about rough paths on Banach spaces. So as I mentioned, the only thing that really doesn't have some work from our previous definitions is that we need to actually specify a tensor product. So if we define just a tensor product algebraically, we get finite sums like this. And the problem is that this is not we need to complete it into something with respect to some norm. So the standard idea to get something that's well behaved is to assume that your norm on the tensor product is what is called a reasonable cross norm. Meaning that if you take the tensor product of two things, it is the product like this. And the same relation holds if you use the operator norm on continuous functions. And the largest source norm, or the one that gives the smallest extension, however you want to extend it, think about it, is called the projective norm, which is that you see all the ways you can write an element in the algebraic in the algebraic tensor product, all the ways you can write it as a finite tensor product, and then you take the incremental lengths of all of these. And then you define the tensor product as the completion with respect to this norm. Once we set all this up, all the definitions of rough paths are then ready to be used. So let's do the concrete example which we're going to look today, which is what happens when E is a Hilbert space. So when E is a Hilbert space, it will be very convenient for me to not to use the standard notation of the algebra, but the exponential coordinates, meaning that I take something that's written in the tensor algebra like this, and I only look at the first order part plus the antisymmetric part of the second order part, because yeah, I'm already just working with weakly geometric rough paths, so the symmetric part is already determined. So I can consider all things that are happening in the weakly geometric case as something that happens in E and then the wedge product square of E. And I just use this identification to make the multiplication work. And then in this setting, 0 will be the identity. So I'll try to use Y when I write things like this and X when I write in this notation. So since we have a Hilbert space, we can use this Hilbert structure to show that any element here in the wedge, the algebraic wedge, is some finite sums of elements like this, where all of these vector fields are unit vector fields and mutually orthogonal. And this is a decreasing positive sequence. And then the projective norm in this setting is what's called the Schatten-1 norm, which is you take all of these and just sum them, take the L1 norm. And why is it called the Schatten-1 norm? Because you can identify this with skew symmetric operators of the Hilbert space to itself, and then this becomes the singular values of that operator. And so in our closure, all of the elements in the tensor product will be basically things like this, where the sum over here has a finite L1 norm. So this is, now we know what the rough path is. So let's see, now we need to turn to Konoka-Theodori geometry. So recall that what we want to show is that we want to be able to approximate weakly geometric rough paths with passive boundary variations, or yeah, you can even go smooth. So we need this. The standard thing of how this is done in finite dimension is that you replace your distance, which we have here and we used, with a distance that is geodesic. So recall that if you have a metric space, then it's a geodesic if you can connect every 2 points by a geodesic. That means that you have some curve going from one point to another, and the distance of the curve is exactly the distance between them. And also, if you go any further apart, then the length is actually just the length of the interval times this thing here. The reason you want this is that in geodesic spaces, you can approximate all continuous curves with geodesics or piecewise geodesics in the sup norm. So this is really nice. So the standard, the thing you want to pick in the finite dimensional case is called the Konoka-Theodori metric, and it's defined in the following way. So you basically take any point in the path that the weakly geometric curves reach, and you say, what is the smallest length that I can define? I can use a curve of boundary variation I can reach the same point. So I have a curve boundary variation. It goes from 0 to this point here. And its integral is exactly what you want in the second order term in the tensor. So what is the smallest length I can have from this? So the properties of this metric that it has in finite dimension is that for anything in the space where the weakly geometric rough paths take their values, the distance will be finite. This is called the Shawara-Sefsky theorem. And since it's defined like this, it's a length space. So the Hoff-Riemann theorem then tells us that it's geodesic. Well, you need to show that it's complete, but it's this works out in this case. And the D metric and the rho metric will then be equivalent in this case, so you can replace them, hold their maps, or still the same. So if we go to the infinite dimensional case, we lose all of these. So if we want to prove something like this, we need to get around the fact that we don't have any. The Hoff-Riemann theorem doesn't work because we're not locally compact. Shawara-Sefsky doesn't really exist. In Hilbert manifolds, it tells us that we can reach a dense set, but that's about it. And generally, these metrics will not be equivalent. So let's just show concretely what happened with this Kanoko-Theodori metric is in the case of Hilbert spaces. So I will use the formula for the metric is generally kind of complicated, but we can show that it has this equivalence with respect to a bit of a simpler metric. So we computed this, that it's equivalent to using the normal inner product on here, and then using a slightly different kind of norm on the second order part. So rather than, so recall that anything here, since we use these exponential coordinates, we can write anything as like a wedge product here, where all these are unit orthonormal vector fields. And what we need to do is we need to order them in decreasing order, and then the first one counts once, second one counts twice, and so forward. So this will not be norm, it will be quasi-norm. That means that it's, more precisely, it doesn't satisfy triangle inequality, but its square root does. It's bounded between the Chapman 1 and what will happen if you take Chapman 1 half. This looks a bit strange from the definition, but because it seems like it would not be bounded by any such norms, but because you have this idea that these things have to be decreasing, you actually get this inequality. In particular, there will be like this distance here will not be finite for any point in our space. So for example, if I take something here that decays like 1 over j square, then it will be finite in the Chapman 1 norm. So it will be in our tensor product, but it will not have finite Kanoko-Theodori distance. We replace, so in order to get something that works in an infinite dimensional setting, we introduce the following criteria that we have to have satisfied, namely that our distance has to be bounded from above by the Kanoko-Theodori distance, that on the set where this distance is finite, the distance has to be also the set containing the identity. The distance has to be a geodesic space, and then finally that the weakly geometric rough paths, which take values in this space and are continuous, they have to be dense in a larger space if I go up. If I adjust the Holder exponent a little. So basically, rather you can think of it this way, then rather than considering the signatures of curves of boundary variation, this result says that if I have the first two, I'm allowed to prove density with respect to a larger class of function. So note that this set, in the Hilbert space setting, this set B infinity will be dense, but not everything. Furthermore, it's important to note that any weakly geometric rough path that takes its values in this space is not necessarily continuous. So we explicitly construct an alpha 1 Hölder 1/2 path in this that has values in this space. That's Hölder 1/2 with respect to the d distance, so the normal distance, but will not be continuous with respect to the Canonical-Theodorian norm. So you need to be a bit careful when considering this class. All that remains to do in order for us to prove the results that we wanted is to show that these things hold on Hilbert spaces. So we showed explicitly earlier that because this CC quasi-norm is larger than the Schatten 1 norm, it will bound the other norm from above. Then we need to show that this space is geodesic, and we basically use that for everything in the algebra, that is the algebraic tensor product, we actually have a geodesic, and then we just need to enclose it into a compact space. And then we show that their midpoints converge. And having a midpoint between 2 points, that means a point that has exactly 1/2 distance from each of the two endpoints, is equivalent to having to being a geodesic space. So so this part is the truly awful part of this. This is the paper, because it doesn't really convert. It's not compact in the correct metric, and you need to do a lot of hacks to make it work. But it does. Like this is the, and then for the last part, you can use some projections and some brute force to show that, okay, yeah, this is actually the case. These other paths are close. And this gives us our result. So for the remaining 3 minutes, let me speak about some applications. So what you want to do, so one of the applications is the application to rough flows that is introduced by Ismail Bayel and his collaborators. So the idea is basically you have something like you want to define a local flow of a time-dependent vector field, only that your time-dependent vector field is rough in a certain sense. So you want to have a rough version. So rather than looking at, if you think rough path is a generalization that contains paths of stochastic processes, then this is a generalization that contains stochastic flows in a certain sense. So it's been, you can consider these, so I will give references in 2 slides and I will give some more details. You can, there's a connection between these rough drivers and rough paths in the space here of C3 maps. And the relationship is given like this, where you have one spatial derivative here in the first order, and here you have this term, the one second order spatial derivative and one first order spatial derivative in the other setting. And using our now rough path theory, we can get the Wang-Sakai type results, where we say that if we have a rough path that's in the sublevel space for K sufficiently large so that this is inside the space with 3 continuous derivatives, then we have that any solution can be approximated by a solution set of boundary variation, as long as we adjust our Holder exponent. So meaning that we can use this to approximate flows in a certain sense, as long as we have something that comes from a driver that comes from a Hilbert space. So let me just say a little bit about the references and go back to the previous slides a bit. So these rough flows was introduced by Bayer in this paper. Is also more detailed with Bayer and Riedel. In the way that you can recognize these rough drivers as rough paths in continuous functions or continuous self-endomorphisms was described by Kongi and Nielsen in this paper here. And part of what they do in this what Bayer and Riedel do in this rough flow paper is that they show these Wong-Sakai results in the special case where you have some martingale structure, or you can use some stochastic analysis to show that this is true. And so this kind of result kind of gets around this, where you don't really need any stochastic behind it, because you can just use properties with weakly geometric rough paths and rough paths. Yeah, also like to mention the result of Ricci and Serre, which has something describing these distances on, well, in the finite dimensional case of Hilbert spaces. So I described this, what the kind of categorical distance looks like in Hilbert spaces. So in the result in the finite dimensional case is also found in this paper by Ricci and Serre in the appendix. So then I think I did honors to everyone, and I'm done. So thank you very much.